Okay, hello. Do you hear me? Okay, so let's start Count Architecture 1, and this one is also broadcasted through the YouTube, so you can look at the YouTube also. Okay, so last week, actually, we look at what kind of components are available in the computer systems. So now today we look at and also last time we looked at how to measure the performance, right? So today we'll continue about this performance measurement. Okay, so before we are continuing the performance measurement, we'll look at the CPU clocking. So as I mentioned, there is some component, right? In the main component is a processor, CPU, and there is a memory. Okay, and CPU is reading memory data, and then it is executing some instructions. So in order to do that, we have to provide some pulse, like a pulse, like a 0 or 1 value. It's like a heartbeat. So this pulse is called the clock. Okay, so this 0, 1 value is called the clock. So the number is actually determining the performance of the processor. So if we are providing the more clocks per second, then the CPU processing performance will be improved. Okay. So not only for the CPU, actually almost every hardware component is governed by the clock, constantly clock. Okay, so the performance of the processor is depending on the number of clocks. So let's look at the clock. So clock is just 0, 1 value. Okay, so let's say this is 0. So lower voltage, this lower voltage, it's low voltage. We are saying this is 0 value, and this is higher value, high voltage. That is used for the 1. Okay. Then the clock is actually the oscillating between 0, 1 values. Okay. So generally the low voltage means it's like a 0 voltage, and high voltage means it's depending on the processor. It was 5 volt, but it is reduced to 3.3 voltage, and it is reduced to 1.5 voltage. It's a varying. So let's say this is 2 volt, for instance. Okay, so the clocking is oscillating between low voltage and high voltage. Okay, so then it is the clock, I mean the voltage is 0, and then it is changed to 1 here, and then it's reduced to the 0. So this is 1, and this is 0, and this is 1, and this is 0. Okay, this 1, 0, 1, 0 duration is called clock period. So this duration is called clock period. Okay. So let's assume that if this clock period is 1 nanosecond, it's 1 nanosecond, which means, so the duration is 1 nanoseconds, then, so this is clock period. We can define clock frequency. So frequency is just inverse of the clock period. It's inverse of clock period. So If clock period is 1 nanosecond, then what about the clock period frequency? If this is 1 nanosecond, what about this value? What's the 1/1 nanosecond? So here it's like this. If the clock period is 1 second, then clock frequency is, for the frequency, we are using hertz unit. Okay, so 1 second means it is 1 hertz, and 1 millisecond, then it is 1 kilohertz, right? And 1 microsecond is 1 hertz, and 1 nanosecond, then it is 1 gigahertz, right? So this is 10 to the minus 3, 10 to the minus 6, this is 10 to the minus 9. It's opposite. 10 to the 3, 10 to the 6, 10 to the 9. Okay, so yeah, that's correct. So 1 nanosecond clock period means the clock frequency is 10 to the 9 hertz, so which is 1 gigahertz. Okay, so maybe you are, sometimes you can see some advertisement about the processor. So your processor is supporting like a 2 gigahertz. This means it's clock frequency. Then what about the clock period in this processor? Yeah, 0.5 nanosecond. So 1 clock period, this is 0.5 nanosecond. Okay, so that's the definition of the clock period and clock frequency. Okay, so we already know that what is clock period and what is the clock frequency, right? So this is clock frequency period, and this is clock frequency. Okay. Maybe you don't have any feeling about how short time of this 1 second, right? So you don't know the 1 nanosecond is how fast, how short. Do you think if the light, how far does light go for 1 nanosecond? Do you think? So how far? Where does light go? So yeah. So we know that the light is transferring like 300 kilo, no, 300,000 kilometer per second, right? So we know that. So this much is, this is 3 with 10 to the 5, 10 to the 3 meter per second, right? So 3 by 10 to the 8 meter per second by 1 nanosecond, which is 10 to the minus 9. So which is 10 to the minus 1 meter. So which is 30 centimeter. So during the 1 nanosecond, even light can go to the 30 centimeter. Okay, so the 1 nanosecond is very short time. Okay, so we know that what is clock period and what is the clock frequency. Then let's look at the CPU time. So last time we looked at we have to measure the time, right? So we are measuring the performance. right? So we are measuring the performance. So performance means that we are measuring the end-to-end time. So we are starting the program and how much does it take to finish that program. And during that time, it is including the CPU time and the other components like memory access and some others, right? So we are only focusing on the CPU part. So we are measuring the CPU time. So CPU time means here we have a processor. So processor CPU. And we are providing the program A. So it has a lot of instructions like it's code. And we are giving this code to the processor. Then processor is learning that program, right? Okay, so processor is learning each instruction, each code. Like this is plus and this is minus and this is like a multiplication. So it's executing. So it's executing. Then so to finish this program, for instance, we need some cycles, right? So we need CPU cycles to finish program A. So for instance, it requires 1,000 cycles, for instance. And we know that CPU clock cycle. Clock cycles. Clock cycle means its duration. So clock cycle is like a 1 millisecond, for instance. Then, so these two values are given. To finish the program A, it takes 1,000 cycles, and each cycle it requires 1 millisecond. Then, to finish program A, how much second do we need, or what's the CPU time for this program? Yeah, 1 nanosecond, because 1,000 cycles, and each one is 1 millisecond, so which is 1 second, right? So 1 second. Okay, so we know that then CPU time is proportional to the number of cycles, right, per program, and clock period, right? So we know that these two things, two parts. So to reduce the CPU time, either we are reducing the number of cycles or we have to reduce the clock period, right? So clock period means we have to increase clock frequency, right? Okay, so this basic thing. Then let's look at this number of clocks. Number of clocks. Okay, as I mentioned, to execute program A, there are many instructions. So here is a plus, minus, multiplication, plus, and there are a lot of instructions. So number of cycle means we need to execute some number of instructions. So instruction means it is including addition, subtraction, and many operations. This operation, number of instructions is operation. And per each instruction, we need clock cycles, right? So per instruction, we need cycles. So for instance, to execute one addition, like A plus B equals C, to execute this one, we need 2 cycles. Or D is C multiplied A, is it takes 5 cycles, for instance. So this case, the cycles per instruction is 2, and lowercase cycle per instruction is 5, right? So the number of cycles are depending on the number of instruction to complete the program A, and also cycles per instructions. So this is cycles per instruction. So briefly, we are saying it's a CPI, right? Okay, so finally, the CPU time is number of instruction per program. So for instance, to execute program A, we need like a 100 instruction, right? And per instruction, we need cycles, right? 2 cycles or 5 cycles. And per each cycles, we need time, so clock period. So that's the CPU time. So for instance, to execute A, we need, so it is generating the 500 instructions to execute the program A. And CPI is 2. And clock period is 2 nanoseconds. Then what is CPU time? So 500 instruction and CPI 2, that means multiply 2, that is number of cycles to finish. And for each cycle, we need 2 nanoseconds, that is the CPU time, so which is 2 milli, not the millisecond, it is 2000 nanosecond, which is 2, what's the unit of that? So nanosecond is 10 to the minus 9. Millisecond is 10 to the minus 3. What's the 10 to the minus 6? Yeah, microsecond. So US or microsecond. Okay. So do you have any question? So you can understand, right? What's the CPU time? How we can compute the CPU time? Okay. So to improve the performance, what we have to do is that first, to decrease number of instructions. So we have to reduce number of instructions, or we have to reduce CPI, or we have to reduce clock period. Okay. Does voltage relate to the CPU time? Actually, we will learn about that. If we are increasing voltage, then we can increase frequency. So it is related to the CPU time, but actually, at this moment, voltage is not related to the CPU time. So CPU time is only related with the clock frequency and number of instructions and cycles per instruction. So voltage is not related to CPU time now. But later we will look at it. Okay. Any other question? No? Okay. Then, so how we can reduce the number of instructions or CPI or clock period? So that is actually the main goal. Okay. So actually, we will look at this part, but let's look at the last one, clock period. So how can we increase clock, decrease clock period, or increase clock frequency? We just increasing the clock frequency, right? Reducing them means we are just increasing the clock frequency. So to increase the clock frequency, what we do is that maybe we are shrinking the size of processor. So shrinking the processor, where we are developing the new technology to implement the processor. So maybe reduce the line width of the processor. And we can increase the clock frequency. So this is related to the hardware part. So this is hardware. So implementation, hardware implementation. CPI, instruction cycle per instructions. So CPI is related with processor architecture. So if we are designing the good architecture, then maybe per cycles we can execute many instructions. Okay, so it depends on the process architecture and number of instruction. That is depending on the instruction set architecture. So we'll learn about that. So if we are providing the many instructions, then maybe we can generate the small number of instructions per program. Okay. CPI and IPC, the same thing. It's opposite. It's inverse. So CPI is 1 over IPC. Okay. So CPI means per instruction, how many, to execute one instruction, how many cycles are required. Instruction per cycle means per cycle, how many instructions we can execute. So it's just opposite. It's inverse relation. Okay. It's just opposite. Inverse relation. Any other question? That's good. So let's look at some CPU time example. So we have two computers, two processors, CPU A, and there is a CPU B. CPU A case, clock frequency is, so how much is it? 2 gigahertz. And then we have a program P. So we are running this program on this process A. Then it takes CPU time is 10 seconds. Okay. So then we are running this program P on the process B. But what we are trying to do is that we are increasing the performance. So CPU time aim is 6 seconds. So in that case, what about the clock frequency to achieve 6 seconds? So can you compute now? What's the answer? Mhm. Okay. So what about the other students? What is your answer? So we know that CPU time is proportional to the clock period, right? So which means it is proportional to the clock 1 over the frequency. So clock frequency is increasing, then CPU time is reduced, right? So we know that. So here, originally CPU time is 10 seconds, and clock frequency is 2 gigahertz. Then now it is aiming to the 6 second. Then what about the X, right? So then the answer is 10 to the 12 over 10, which is, what is it? Not this one, right? What is X value? Right? Okay. So it's now this one. So now we are changing the problem. Okay, so here in this case, CPI was, what is it? Okay, CPI was 1. It is CPI is really increased 1.2. So then what about the clock frequency in the case? It is also same, right? CPU time is proportional to, so in this case, number of instructions are equal. So CPU time is proportional to the CPI and clock period. So which is CPI frequency. Okay, so it was 10 seconds and CPI was, how much is it? It's 1 and 2 years. Then 6 seconds and X and CPI is 1.2. So X is, yeah. How can you compute? Then it's 4, right? X is what? 0.2. So 4 kHz. Right? Okay, so then let's get some another example. Let's say this is the same, everything is the same. Now it is, clock frequency is 2 gigahertz, and CPU time is 5 seconds, and CPI was, it is 2. Now, clock frequency is 1 gigahertz, and CPU time is 10 seconds. In that case, what of the CPI? What about the other students? Two? Yeah. So 5 to the 2 over 2 equal 10 to the 1 over x. So x is 2. So CPI is 2. Right? So now you can understand what's the CPU time, how we are dividing the CPU time into multiple components, right? Okay. So we already look at the CPI things. So here that relationship is there. Okay, so this CPU time is proportional to the clock cycles, CPI, and number of instructions. So number of instructions. Okay, so number of instructions is depending on the instance set architecture or the compiler. So for instance, we are making the C program like A equal B BC plus DC. Okay, so in that case, we can generate a program like this. First, T1 is B multiplied by C, T2 is D multiplied by C, and then A is T1 plus T2. So we need 3 instructions, right? The other one is we can change this program to A equal B plus D multiplied by C. So in that case, T1 is B plus D, A equal T1 plus C. So in this case, we need 2 instructions. So even for the same instruction set architecture, what kind of code is generated by compiler, the number of instructions are different. So the instruction count or number of instructions are depending on the compiler techniques. Okay. So it's totally depending on the compiler and what kind of instructions are available to utilize by the compiler. Okay. And CPI case is depending on the CPU hardware. Okay. If we are utilizing more hardware resource, then maybe we can improve the CPI. So to execute one instruction, maybe we can reduce the number of cycles. Generally, per each instructions, the number of cycles may be different. So as I mentioned, for instance, add, it requires 2 cycles, multiplication is 5 cycles, or division is 100, 220 cycles, right? If we are looking at the program P, it has 10 plus 1 multiplication, like 5 multiplication. Then what about the CPI, average CPI? So let's assume that, okay, what I'm saying is that there is a program has this kind of code, A equal B plus C, and B equal A plus D, blah, 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 and so another sum. There are 10 plus operations, and there is a operation which is multiplication, like a 10 multiplication, 5 multiplication. And let's assume that for the plus, the CPI is 2 cycles, and multiplication, it takes 5 cycles. Then what about the average CPI for this program P? So what about the total cycles? For the total cycles, there are 10 plus operation, which takes 2 cycles, and 5 multiplication, which requires 5 cycles. So total is 45. And number of instruction is 15. So it is 3. So that's the, okay. So this is average CPI. If we have another program, like a Q, so everything is same, but program is different. So here in this case, plus is 5 plus, and there is a 15 multiplication. Then what about the average CPI? So what about the total cycles? Yeah. 85, right? Because there are 5 addition and CPI is 2 and 15 multiplication and CPI is 5. And total number of instruction is 20. So 4.25 CPI. So CPI is not only depending on the hardware, it is also depending on what kind of program you are learning. Okay, so if we are learning short CPI instruction, then maybe the average CPI is small. If you are learning the long CPI instruction, then the CPI will increase. So CPI is dependent on hardware and the program software. Okay, so we cannot say this processor CPI is like this. Okay, so like a Intel 2 gigahertz machine case, the CPI is 2. We cannot say that. If we are giving the specific program, then we can say for this program on this machine, then CPI is like this. Okay, so we can say that answer. Okay, so let's look at CPI example. It's similar to the previous example here. There are 2 computers, processor A and processor B. And clock cycle is 250 picosecond, which is 0.25 nanosecond. And CPI is 2. And here, clock frequency, clock cycles is 500 picosecond. So 0.5 nanosecond. Same thing. And CPI is 1.2. So what about the performance of this processor in A and B? So which one is faster and how much is fast? Which is faster? How much is it fast? A, how much? 1.2. Okay, so how can you compute? So what we are assuming is that processor A and B are executing the same number of instructions, right? If both processors are running different instructions, then we cannot compare the performance. So what we are showing is that same number of instructions for both processor, right? So let's say this is n instructions. Then what about the CPU time of A? If number of instructions is n, then the CPU time is n multiplied by 2, 1 over the 250. This is CPU time. CPU time B is the same n, and CPI is 1.2, and not this one. It is 500. Yes. So that means this 500n, and this is 600n. So A's CPU time is shorter. So A is fast. A is fast. How much? Yeah, this much times fast. Okay. So any number is given, you can solve it, right? Let's say it is 1 nanosecond. And psi is 1.5. And here, this one is 2 nanosecond. And CPI is 3. Then, which is faster and how much fast? So A is faster or is the same? What about the other person's opinion? How much fast? Yeah. So as I mentioned here, CPU time is proportional to the number of instructions and clock cycles and CPI. So here in this case, n times 1.5 times 1. And B case, CPU time is n 2 and 3. So this one is 1.5 and this one is 6n. So A is faster. How much? By 4 times. Right? So A is faster than B. So by 4 times. Okay. So now you're understanding about the CPU time, and also you also know about the average CPI, right? Okay, so let's look at this example, CPI example. We already see that. Here, we have 3 instructions. So A, B, C instruction. For instance, this is addition, and this is like a multiplication, and this is division, for instance. Okay. So for each instruction set, the CPIs are different. For A, it takes 1 cycle. For the B, 2 cycles. C is 3 cycles. Okay. And also we have 2 programs. This is program 1, and this is program 2. Okay. So program 1 case, it has some instruction. So A, add instruction is 2. Number of multiplication is 1. Number of division is 2. Okay, so 2, 1, 1. And the other problem case, addition is 4, multiplication is 1, division is 1. So in that case, what about the average CPI? So let's look at the average CPI for 1. So what about the first program? What's the total number of cycles? It's 10 because A, 1 cycle, there are 2 instructions. B, 2 cycles and there is 1 instructions. And C, 3 cycles, there is 2 instructions. So total is 10. And how many instructions for program 1? 5. 2 plus 1 plus 2. So 2 plus 1 plus 2. This is 5. So CPI is 2. So what about the second one, program 2? What is the CPI, average CPI? Total number of instruction. So total number of instruction is 6. And cycles are 9. So it is 1.5 CPI. Okay? So even for the same hardware, same processor, if we are running the different program, then the CPI is changing. Okay. Okay. So let us summarize the performance measurement. So as I mentioned, the CPU time is proportional to the number of instructions, CPI, and clock cycle. Okay. So number of instructions, CPI, and clock cycle. Okay. So number of instructions are depending on what kind of compiler we are using, right? So compiler is affecting the number of instruction. And some case it is changing the clock per instruction. CPI also changing. And if we are changing the algorithm like a bubble sort or is quick sort, then the total number of instructions are different. So totally the number of instructions are different. Possibly CPI is also changing. Program language like a C or like a Python, definitely number of instructions and CPIs are different. Okay, different. And instruction set architecture, which means that we have defined what kind of instruction set instruction. So what kind of instruction is supported, then it is changing the instruction number of instructions. So for instance, if the processor is providing the very complicated instruction, then maybe you can reduce number of instructions. Or it is also changing the CPI part and also the clock frequency or clock period. Clock cycle. Clock period same as clock cycle. Yes, clock period is actually same to the clock cycle. Clock cycle is a clock period. Okay, the same word. Any other question about the performance measurement? So now we are just focusing on the CPU time only. Okay, so then later we will look at, so in the next chapter, we learn about the instruction set architecture, right? The instruction set architecture is affecting number of instruction and CPI and also clock period or clock cycle. So it's a very important part. Okay, so then now we are looking at the power trend. So as I mentioned, CPU time is proportional to the cycle, right? Which is 1 over clock frequency. So which means that if we are increasing the clock frequency, then we can improve the performance of the processor right? So we just increasing the clock frequency. Increasing, then CPU performance also increasing because CPU time is decreased. So simply we are increasing the clock frequency, then easily we can improve the clock frequency performance so that the clock rate, so clock frequency in the y-axis, there is a clock rate, right? So clock rate is increasing. So clock rate it was 12.5 megahertz, 60 megahertz, 25 megahertz. So it's keep increasing to 1,000. So it's 2 gigahertz. 2 gigahertz. So 2 gigahertz and 3.6 gigahertz. After that, what is happening? So what about the next? So after 3.6 gigahertz, so increase the clock frequency means that the performance is improved, right? So what about the next then? What about the here? Clock frequency is not increasing, right? It's stable or a little bit dropped. Do you know why? Why we cannot increase in the clock frequency anymore? Do you guess? Yeah, because of heat and power consumption. So let's look at this power consumption, so energy consumption. So the energy is increasing, right? If the clock frequency is increasing, energy consumption is increasing also. So at that moment here, it was 100 watt. So 100 watt. How? If we are looking at the bulb, then this I think is 25 watt, right? I think. So which means that per processor, just small processor, is requiring the 4 bulbs. It's consuming that much. So if we are, I don't know, you can, but if you are touching the bulb, then it's very hot, right? So it's very hot. Processor is the same. When 3.6 gigahertz case, the temperature of this surface of processor is like 100 Celsius. It's like it's more than 100, like this. So at the time, it's possible to egg fry on this processor, where you can boil the waters to make some noodles. So that is possible. So the heat is too much. So which means that if the processor is reaching to the 100 Celsius, then the processor is not working properly. So later, instead of increasing the performance, actually the performance a little bit dropped, right? The clock frequency a little bit dropped, and it's keep going. I mean, they are trying to reduce the energy consumption. That's what they are doing. So reducing the energy consumption means that we can reduce the heat emission. So we can reduce the heat, and also the saving the power consumption means that if we are using the smart device like a smartphone, we can save the battery, right? So low voltage means that low temperature and long battery life. So the battery life is very important, right? Battery time is very important for the mobile devices. So instead of increasing the frequency, they are trying to reduce the power consumption by reducing the frequency. Then why reducing the frequency or reducing the voltage is solving the problem. Okay, so let's look at this one. Let's look at the transistor. Actually, transistor is a kind of a switch. Switch means that is connection and there is interconnection. So we can close or open. Okay, close and open. So when this is open means it's 0, close means it's 1. Okay, so that's transistor. So transistor, how we can make a transistor is that using MOS. It's like this. There is a silicon and there is metal and there is another metal and there's interconnected. And for switching, there is metal material and this part is like a switch. So if this is plus, then this part is plus, and then the electron is moving to the surface. Then in that case, if we are giving some voltage to this metal and the other metal, then the electron can flow to this direction. Okay, because the electrons are very gathered on the surface area, so that there's plenty of electrons to move from one metal to the other. So this is free metal and free electrons, so that this is kind of closing the circuit. It's just like a closing circuit. It's like 1. If there's no voltage, then there's nothing. So electrons are just dispersed in places. So in the case, if this is minus and this is plus, then so this one is just only going to this part. So there is only minus. So minus is trying to go in that place and go in this place, and here there is minus is there, but there is some gaps between here. And there is a gap. So the electron cannot move this gap. So that this is like a open circuit. Okay, this is open. So clock frequency means that we have to remove these electrons from this part, or we have to insert the electron to this switch. So frequency is proportional to the how fast we can extract or insert electrons in the circuit, in the transistor or switch. Okay, so which means that if we are using the high voltage, so this is if we are giving the high voltage, then the electron moving is much faster, right? So high voltage means electron moves fast. If the voltage is lower, then the electron is moving much slower. So it's just proportional. So the voltage is proportional to the clock cycle. So if we are providing the higher voltage, then clock cycle is reducing. If we are providing the low voltage, then clock cycle is increasing. So higher voltage is small cycles. It's the clock frequency. Okay, so we know the voltage is proportional to the clock frequency. The other one is, let's look at the power. So I think in high school you learn about the voltage, current relation, right? And resistance. So voltage is current multiplied by resistance. You know that, right? And power is defined by voltage by current. That's the power. Okay, so power is voltage, and I equal actually all over V. So it is V R. So R V squared. Okay, so power consumption is proportional to the square of voltage. Square of voltage. So which means that if voltage is 1 volt to the 2 voltage, then power consumption is voltage. Power consumption is it's like 1 watt to the 4 watt. This power consumption. Because the resistance is not changing. It's like a hardware part. Okay, so which means that if we are increasing the voltage, what about the frequency? So 1 voltage case, maybe it takes 1 gigahertz. And if we are providing the 2 voltage, then what about the clock frequency? Can be possible. So voltage is increasing, then clock frequency is proportionally increasing. It increases like a 2 gigahertz. Okay. So let's say if program takes CPU time it is like a 10 second, then what about the 2 voltage case? What about the CPU time in the case? If the clock frequency was 1 gigahertz, yeah, it is 5 seconds. 5 seconds. Okay. What about the energy consumption? Energy is power multiplied by time, right? So that's the energy. This is energy. Okay. So then what about the energy? So power is 1 and time is 10. So it's like a 10 watt something, right? What about the 2 volt case? What about the energy consumption? Yeah. Power is 4 and time is 5. It's 20. So if we are running the one program, if we are running on the 1 voltage, it consumes like a 10 watt. If we are increasing the voltage, then we need 20 watt, right? Even for the short time. So then which is consuming more energy? Definitely high voltage, right? So to execute one program, higher voltage is consuming more energy, which means that it is emitting more heat. Okay, so that's the energy power voltage relation. So that means if you have a program, CPU, so you have a processor and you are running the program, so your program is just utilizing the 50% of the CPU time. Okay, which means that among 10 seconds, only 5 seconds is working and the other 5 seconds is idle, nothing is executed. So this is better or during the 10 second. Okay, so let us do that this case. So we have a CPU. So this case it is 2 voltage and it's running program. Okay, so program is running 50% time and 50% there's nothing. Okay, and another processor is 1 voltage and it's a program and it is utilizing 100% of the CPU. So which is better, do you think, in terms of energy consumption? Which is better? So better means that which is consuming less energy. Which is consuming less energy. So as I mentioned, process A case, the power consumption is like 4, right? Because of its 2 voltage. And B case power consumption is 1 because power consumption is proportional to the voltage square, right? Then A case it is consuming this much, and then there is nothing. So during the 5 second, it consumes much, and 10 seconds there's 0, and this is 20. And B case, during the 10 second, it is consuming the power. So this is 10. So which is consuming less energy? Yeah. So B is consuming less energy. So which means that if we are reducing the voltage, then we can improve the battery life also. So it means that you have a laptop, right? You have a laptop. Notebook machine. In your notebook machine, there is a processor. There is a processor. If we are running the small program, just simple small program, then maybe it is consuming less energy. But if you are running heavy program, like a heavy program, then it is consuming much more energy. Okay. So here in this case, just a single case, it is 1 watt. In this case, even though this there is 2, but voltage is improved, so increases, so it is consuming square watt. So that's the reason why modern processor has changing processor voltage depending on workload. Modern CPU is providing the dynamic voltage frequency scaling. So if there is a less work, then automatically it is reducing the power energy voltage level. So it is decreasing the voltage level if there are many work to do, then it's increasing the voltage so that it is emitting a lot of heat. So the power consumption is so large at the case. So it is changing the voltage, adapting on the workload. Okay, so for the multiprocess part, yeah. So instead of increase the performance, I mean the clock frequency, these days what we are doing is that instead of just single processor, we are adding more cores. That's much better, okay? Because improving the voltage, increase the voltage means that power consumption wise, it is 4 times. But if we are adding 2 cores without changing the voltage, so 1 voltage, single core, in that case, power consumption is 1, and double core case is 2. Right? So even the performance improved by 2, the power consumption is just 2. But if we increase the voltage, then the power consumption is 4 times. Okay, but the problem of the process is that making the program developing is very difficult. Okay, so we are skipping over the spec benchmark. Okay. So we are learning about what kind of components are available in the computer hardware, and also we know about that what is performance, right? So performance means that we are focusing on the CPU time, and time has 3 parts: number of instructions, CPI, and clock cycle. So we also learn about what is clock cycle. And power consumption. Power consumption is proportional to the square of the voltage. So that due to the power consumption or heat emission, we cannot increase voltage anymore, actually dropping the voltage. Instead of that, we are improving the parallelism. So we are adding more component to improve the performance. So that's the modern approaches. Okay, so next time we'll continue about the instruction set architecture. And we are doing some exercise, using some lab doing this instruction set architecture. So, okay, any question? Actually, we almost covered. Skip the part is actually we will, it will be appearing again in the next time. So we almost covered everything. Clock rate is clock frequency. Yes, clock rate is clock frequency. It's the same word. There's a clock frequency. Clock cycle is clock period. Any other? Can we watch last week lecture recording? Yes, it is also available in the Blackboard. So if we are going to the Blackboard, I think if we are looking at the Blackboard collaboration, menu, then if we are looking at the collaborate menu, there is this 3-dot menu. So if you are clicking here, then you can see the video clip. All video clips you can see. Using parallelism means using more cores. Yes, that's correct. Any other question? No more? Okay. Then see you on Wednesday. 자, 여기까지 합시다.